I want to talk not about how to apply the relativistic principles of quantum mechanics to the hydrogen atom, but two of the big results that we will talk about at this level of applying relativistic principles to the quantum mechanics of a hydrogen atom. And this isn't a topic you would typically run into until you start getting into quantum mechanics at a graduate level, though I have known a physics professor to actually go through the relativistic version of the Schrödinger equation with their students at a senior level as an undergrad physics major, but that's not what we're here to do today. So when you apply relativistic principles, you end up with a couple of interesting results. One of the results is there are two sets of solutions that mathematically are perfectly valid. One set of solutions involves an energy state of a particle that, based on its inertial mass, would have a positive energy value related to the inertial mass times the speed of light squared with additional energy beyond that. The other would be an energy associated with the inertial mass of minus the inertial mass times the speed of light squared with totally filled unavailable states down there. These sets of solutions are what physicists refer to as antimatter, whereas the solutions that we use are referred to as normal matter. So that'll be touched on in a later chapter in our book. What I want to talk about with this video is a weird result of the quantization of the relativistic system. We end up getting additional angular momentum that appears to be intrinsic not to the electron's orbit, but to the electron itself. Now, an electron is the closest thing that we can think of to being a point particle in terms of massive objects, but it's like the electron has an angular momentum for sort of rotation around itself. And that's what we call the spin of an electron. So all particles have an associated spin quantum number. For some, the spin quantum number might be 0 or 1. If you have an integer spin number, you could even have 2 for some particles. Integer spin numbers are called bosons, or particles that obey Bose statistics. Electrons have a spin number of 1/2. Other particles have spins of 3/2. So if the spin value is 1/2 or 3/2, it obeys a different set of statistics called Fermi statistics, so they are referred to as fermions. So if a spin of 1/2 is what our particle has, which is what an electron has, the spin angular momentum is going to be the square root of our spin quantum number times that spin quantum number plus 1. So that would give me the square root of 1/2 times 3/2 times h bar. So the amount of spin angular momentum, the intrinsic angular momentum of an electron, is the square root of 3/2 times h bar. Now for an m quantum number, the m quantum number has to start at our L value, and we would keep subtracting 1 till we get minus our L value. Well, for values 1/2, that gives us two solutions, plus 1/2 and minus 1/2. So if we were to look at the projection of that spin angular momentum around a magnetic field, one of those spin angular momenta would be projected up, the other would be projected down. So we often refer to these as, instead of plus 1 or minus 1, as spin up or spin down. Now, if we wanted to, we could calculate the angle between the magnetic field and the spin. So the cosine of the angle between our m quantum number and our total angular momentum, here our value of s, is equal to the amount of angular momentum projected along the axis of the magnetic field divided by our total angular momentum. So that's our m quantum number divided by the square root of L times L plus 1. So Here, the angle for our spins would be the inverse cosine of plus or minus 1/2 divided by the square root of 3 over 2. So for spin up, that would be the positive solution, and the inverse cosine of 1 over the square root of 3 gives me an angle from the z-axis of 54.7. Now, if you were to take minus 1 over the square root of 3, you would end up getting an angle of negative 54.7 degrees, but the way that we measure it, we would measure it from the z-axis rotating down through an angle of 180 degrees, so that translates to an angle of 125.3 degrees from our z-axis for a spin down. Thanks for watching.